Okay. Now we prove this Parseval identity to conclude our this chapter. The first result is that if f is piecewise differentiable, because for piecewise differentiable, we know that the Fourier series converge uniformly. Okay, so we consider this easy case first. So a theorem, if f is piecewise differentiable, maybe I will write yes. F is continuous, 2 pi periodic, and piecewise differentiable. Okay, we need to the other condition as well, but I will just write piecewise differentiable. Then Parseval identity is true. Then we have a0 square plus ak square plus bk square is f square x dx. Okay, this is not difficult, very easy. So since f is piecewise differentiable, we know that the partial sum converges to f uniformly by our theorem. Okay, so for a large enough and the x in the interval minus pi, we have Sn x. Sn x will not greater than Sn infinity norm, will not greater than 1 plus f. Maybe this is not a good style to explain this, but okay. So Sn minus f will not greater than the supplement. The supplement is Sn minus f infinity norm plus fx will not greater than the supplement. So that is the infinite norm. But this goes to 0. So when a large enough, this will not greater than 1. So we obtain that this is less than 1 plus. Okay. Then our idea is here. We have known that to prove Parseval identity, we need to prove that this integral goes to 0. We need to prove that this integral goes to 0. So we want to estimate this integral. So we study its integrand. Okay, the integrand Sn square x minus f square x. That is Sn x minus plus fx, Sn x minus fx. And by our previous estimation, this will not greater than less than 1 plus 2f x f in L infinity norm. Then Sn x minus fx. Here S and X plus Fx absolute value will not greater than taking absolute value separately. Then the absolute value of S and X is not greater than 1 plus L infinity norm of F. And the absolute value of Fx here will not greater than the L infinity norm of F as well. Therefore, we altogether have 2 L infinity norm. Okay, so this means that S square Sn square minus F square. This is true for every X. And we also take the L infinity norm of this to enlarge this further. This will not greater than 1 plus 2 F infinity, then Sn minus F L infinity. Because taking supplement for this, we obtain this. Okay, then this implies that because Sn converge uniformly to F, we know that the right hand side goes to 0. Therefore, this means that this inequality implies that Sn square minus F square L infinity, because taking the supplement of this, the right hand side does not depend on X. Therefore, we obtain that the L infinity norm of this will not greater than 1 plus 2 F Sn minus F L infinity, which goes to 0. Because Sn, the F is piecewise differentiable, so the Fourier series of F converge to F uniformly. That is, Sn converge to F uniformly. Therefore, the L infinity norm goes to 0. Okay, so we conclude that Sn square minus F square goes to 0. Therefore, our using this uniformly convergence, we can have this estimate minus pi Sn square x dx minus pi f square x dx. This will not greater than the integral Sn square x minus f square x dx. This goes to 0. This will not greater than the supplement of the integral multiplying the length of the integral. But the supplement of this integral is precisely Sn square minus f square L infinity norm multiplying 2 pi. Then this goes to 0. Okay, so this means that minus pi Sn square x dx goes to minus pi f square x dx. But Sn square, as we observed before, Sn square is here. Sn square integral is the first n term of the square of the Fourier series. Okay, so using the result, we know that this equal half of a0 square plus nk from 1 ak square plus bk square. So taking limit, we know that that is exactly our Parseval identity. Okay, because we already proved this result, we already have this result. But the left hand side is precisely this. So let n goes to 0, this goes to the integral of f square. That is, when summing k from 1 to infinity, the result is the integral of f square, precisely the Parseval identity. Okay, so for piecewise differentiable function, we have proved Parseval identity. The proof of this Parseval identity depends on the uniformly convergence of the Fourier series of f to f. Depending on the result that the Fourier series of f converging to f uniformly. That is Sn minus f. The infinity norm of f Sn minus f goes to 0. Okay. So, but we still need to establish the Parseval identity for general function. The most general case is square integrable, that is f in L2. So we need to extend this result to L2. So this is the next theorem. F in L2, then the Parseval identity is true. And after we prove this Parseval identity, we will have some amazing conclusion. Okay, prove. We have already proved the Parseval identity for piecewise smooth, piecewise differentiable function. So we want to extend this to for general square integrable function. So we consider the simple case first. Firstly, we consider the f is integrable in the sense of Riemann on the interval. Then, for any epsilon positive, we have a partition P of the interval. Of the interval minus pi, such that the oscillation area of f under this partition is very small. Very small. The integrability implies guarantee that this can be true. We require it is so small. Here, omega I is the supplement of f on the ith subinterval minus the infiniment of f in the interval. Okay, this is equivalent condition for the integrability of f. Okay. Now, for the partition P of the interval 0 minus pi minus pi. This is our f, and the partition. For the partition P, we construct a piecewise smooth function. So making the points on the graph of f, then linking them by segment. This is the function g. Okay, so let g be the corresponding piecewise linear function. Piecewise linear function about the partition P. Then we have Gx will not greater than supplement of fx on the interval. This is obviously true. Okay. Because by the definition of G, you can see that this is true. Because the graph of the G is the segment linking some point on the graph of F. So the maximum point and the minimum point of G, the coordinate are the points on the graph of F. Therefore, G could not exceed the supplement of the absolute value of F. Okay, and also this is also true for the in the subinterval. In the subinterval, we also have supplement of f minus g will not greater than the oscillation of f on the subinterval. This is easy. This is easy. To prove this legally, you need to write the expression of G. But from the picture, it is very intuitive. For example, we consider this subinterval. Then the difference of f and g, the largest number is here. Okay, the largest distance from the graph of f and g is here. This will not exceed the supplement of f will not exceed the oscillation of f on the interval, because the f is the graph f is here. The oscillation is omega I. Okay, so this justified this result. This is not a proof. You want to prove this, you have to write the expression for G. This is elementary estimate. But from the graph we draw here, it is obviously true. Okay. If you are interested, you might write the expression for G and then verify this.